Today is September 22nd, 2011. This is AP Statistics at Berkeley High School. And here we are in section 2.2. We're going to look at the normal distribution. All right. So we had started yesterday talking about how we can talk about distributions. We talked about things like percentile scores. How much of the data falls below a particular item in our data set. We talked about density curves, curves that are idealized forms of data distributions, and we can find how much data falls in a particular range of values by looking at the area under the curve and below the axis on a particular interval. But today we're going to look at, I wouldn't say a very special distribution, I'm going to say the very special distribution. Certain things in mathematics tend to be extremely important and tend to crop up everywhere. Maybe sometime in your elementary mathematics career, you notice that this number pi shows up a lot. Pi is a very special number. Maybe later in Algebra 2 or pre-calculus, you encountered the number E, Euler's number. And all of a sudden, it starts popping up everywhere. Those are really, really special values. Well, in the statistics world, this is that special thing. The normal distribution. The most special distribution of data ever. All right. So today, what we're going to learn about is this special distribution. We're going to learn how to describe and apply the 68, 95, 99, 7 rule. We are going to look at what's called the standard normal distribution as compared to just the normal distribution. And we're going to be able to do some normal distribution calculations. Lastly, we're going to try to figure out what's normal. What do we mean by a normal distribution? Can we look at a data set and assess its normality? Ask the question, is this data set a member of this very special distribution, the normal distribution? All right, so let's start with the normal distribution. So first of all, it's a density curve, meaning it's a mathematical description of how data may be distributed. Not in terms of histogram bars, but rather as a curve. Why? Because mathematicians love curves. Attributes of a normal distribution are, 1, they are symmetric. They're even on both sides. 2, they're bell-shaped. 3, they have a single peak in the center. Now, because they are symmetric, the mean and the median occur at the same place. And I'm going to introduce to you a new symbol. I had introduced earlier the symbol X bar, meaning the average, the mean of a data set, but particularly the mean of a data set which is a sample. All right? I can't hear you. Oh, sure. Melissa, would you turn off the lights so people can see better?
Sorry I'm late. Won't happen again.
What time's class start? Okay, I'm going to call you just underneath the bar.
Right.
1 more minute and I would have had to send you down to the office for a special slip. But thanks for showing up, Jason. Danny stole your seat.
I see that.
But, snooze you lose.
All right.
All right, so we have this symbol X bar. It's an average, but I'm going to say in particular is the average of a sample, of a small subgroup of a population. But what if we could find the average of the entire population? We would use a different symbol, and that symbol is the Greek letter mu, spelled M-U. In physics and chemistry, the symbol mu may have different meanings. For us in statistics, it's going to represent the average of a population. If we could interview everyone, what would we get as the average? And because density curves are idealized, meaning as if we could see everything, as if we perfect knowledge. Since density curves represent a perfect knowledge situation, we can pretend that we do know everything. And if the average of that everything is going to be, again, mu, the Greek letter mu. Okay? In the previous chapter, we introduced the symbol S, or S of x, the standard deviation. But in particular, we said, at least I tried to say, that S of x is the standard deviation of a sample, a small group. But what if we could interview everyone and find the standard deviation? We end up with a different idea. We end up with the Greek letter sigma, and we're saying that's our symbol for the standard deviation of a population. Again, using density curves, we live in an idealized world, so we can idealize that we can figure out everything and know the average for everything and the standard deviation for everything. When we know everything, we use these Greek letters instead of our normal Latin letters. Okay, so on to these two diagrams. We have two normal curves. They're both normal distributions. They both...
I apologize for this interruption. For the entire senior homecoming course and the freshman, sophomore, and junior winners of the homecoming, please go to the main doors at this time of the building to work with the band. Thank you.
Okay. Good thing that we'll post this video up later today, all right? So you'll be able to get whatever you're missing. All right? So these are both normal distributions. Single peak, bell-shaped, symmetric. They're both centered at their individual average called mu, and they both have variation. The variation is going to be measured by standard deviation, again, which we're going to call sigma. Now there's one little thing here. Again, I'm not going to talk a lot about what goes on in calculus class, but there is an idea in calculus class that shows up here, and I need to talk about it. And that is, how wide is the standard deviation? Well, if I was a skier, here's me as a skier on top of the hill. All right? I start going down that hill. There's a point where the curve goes from being more steep to less steep. There's a point where it's as if I'm starting to bottom out on the hill. It stops becoming so steep. That point is right there. In calculus, we call it an inflection point. It's a place where the hill goes from being less steep, from being more steep to less steep. The distance from the mean to the location of that inflection point, that's the standard deviation in these normal distributions. Again, okay, this hill's not so high. Maybe instead I'm on a sled. Here's me sitting on a sled on my belly. I go down the sled. About there, it starts to flatten out. I drop down from here. This distance right there is the standard deviation. It's a measurement of the variation in that set. Look at the two sigmas there. The one where the distribution is kind of skinny, the sigma is kind of small. Oh, there's less variation. On the one where the distribution is kind of wide, sigma is bigger. Ah, there's more variation in that data set. Are there any questions about this slide? Hearing none. Let's go on and find some more things out about the normal distribution. Here we go with first idea. First of all, let's give a formal definition. A normal distribution is defined by the normal density curve. The normal density curve, by the way, has a mathematical notation definition. It involves E. It has a place for the mu and standard deviation to go, and you do not need to know it. You do need to know that it's a real curve. It's a real function. You plug a value in, you get a value back out. Right? Based on the sigma and the mu, it's going to be shifted. Based on your mu, it's going to be wider or skinnier based on your sigma. Right? The normal distribution is symmetric. So the mean is at the exact center of the distribution. Or we could say that the mean and the median are located at the same place. And as I said before, standard deviation is this location on the normal curve where there's a change in curvature, where it goes from being more steep to less steep. The distance from the mean to that location is the standard deviation sigma. And because a normal distribution can be described completely using the two numbers, the mean and the standard deviation, we have a shorthand notation. We don't have to write a normal distribution with mean 65 and standard deviation 2.5. We don't have to write that out. We can just say, oh, we're talking about a normal distribution? Use the letter N. Where's its mean? Oh, its mean was at 65. Where's its standard deviation? What was its standard deviation? Oh, it's 2.5. That notation completely describes the entire distribution. Now, I've spent a lot of time talking about just this one family of distributions. Why is it so important? It's so important because it shows up in nature all of the time. You look at the distribution of heights among young females in America. That distribution of heights is normally distributed. Single peak, centered at the mean. Same thing with male heights. If you look at natural phenomena, the normal distribution shows up all the time. All right. Does anyone require any more time on this slide? Nope. So normal distributions are good descriptions of some distributions of real data. Also, normal distributions are good approximations of things that happen randomly. Anybody watch Price is Right? One person watches Price is Right. Not religiously.
I watch it every day.
Every day. You love Drew Carey.
Yeah.
Drew Carey better than Bob Barker?
No.
Yeah. Hey, he's asking me now.
No. All right. Paul? Bob Barker, Drew Carey. Which one? Okay. Now the reason why Drew Carey, the reason I bring up Price is Right is because there's a game in the Price is Right that actually, if you did it again and again and again, the distribution of where some random phenomenon would happen is described by the normal distribution. The game I'm talking about is Plinko. Plinko game? In Price is Right? You drop the little disc down, they go and then land somewhere in the bottom. If you do that again and again and again, the distribution of where those things land has a single peak, bell-shaped, assuming that you always drop it directly in the center, as you should. It is a random phenomenon, but its result shows up as a normal distribution. All right? Let's go to the next slide. Now, what other things does normal distributions have in common? Well, it has something in common called the 68, 95, 99, 7 rule. Every normal distribution, no matter where it's centered and how much variation there is, the standard deviation, always follows this rough rule. Here's the idea. Look at this beautiful normal distribution. Do you see that big light blue clump in the center? Now, the number of occurrences that happen in that light blue center is related to the area under the curve and between those intervals. In all normal distributions, there is about, oops, come on, show it to me. It's right. There we go. It is approximately 68% of the data. 68% of the data, we say, fall within one standard deviation of the mean. Approximately 68% of the data in every single normal distribution falls within one standard deviation of the mean. Now, let's talk about that in practical terms just for a second. I told you that the heights of young American women are approximately normal. Oh, and for normal. It so happens that the average height of young American women is 65.5 inches tall. 5 foot, 5.5. Standard deviation, right, are all American women the same height? No, there's variation. So there must be a standard deviation. The standard deviation of young women heights is 2.5 inches. Now, based on this rule, where in this particular instance, I'm at 65.5 in the middle, and I go 2.5 inches down to 63 inches, or I go 2.5 inches up, and I'm at 68 inches. What I'm going to say then is, based on this 68, 95, 99, 7 rule, about 68% of the young female population of America is between 63 inches and 68 inches. The vast, vast majority of all women in America are between 5'3" and 5'8". Does that match your understanding? Okay? Let's do a quick check. How many females do we have? Can I help you guys back here?
We got it.
You got it? You don't need any help. All right. So, how many females do we have in this class? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We got 15 females in this class. Did I miscount? I did not. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I did not count all. Okay, there are 16 in this class. All right? There are 16 females in this class. Okay? Please stand up if you are between 5 foot. I'm going to blame it on the technology. There we go. Stand up if you're a female between 5'3" and 5'8". Stand up, please. Okay, I'll make sure I get the number right now. And point to sit down. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So, did I get it exactly? No. But I'm in the ballpark. Said 68. We got about 50%. No, not about. Exactly 50%. Okay. Doesn't work all the time, but we're in the ballpark. All right. So, the first part of this, again, the empirical rule, is that 68% of the population in a normal distribution is within one standard deviation of the mean. Okay, 95% of the data is within 2 standard deviations of the mean. Well, what does that mean in our case? Well, what if I went down another 2.5 inches? I would be at 60.5 here. What if I went up another 2.5 inches, I would be at 70.5. Now I could ask the same question. Out of our 16 females, how many are between 5 foot and 1/2 inch and 5 foot 10.5? Okay, how many are between 5 foot 1/2 inch and 5 foot 10 and 1/2 inches? Stand up if you're in that range. Stand up if you're in that range, and I'll count you off again. And as soon as I point to you, sit down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. How'd I do? 14 out of 16. What percentage is that? I don't think it's exactly 95. 88. Am I near 95? Okay. Who are the two that are not in that range? Okay, you're both on the small side?
Yeah.
All right. Last part of the empirical rule. Approximately 99.7, which is essentially nearly everyone, is within 3 standard deviations of the mean. So what if I go out another 2.5 inches for this example? I am now between 72.5 on the top end, and I'm at 58 inches on the low end. This is 4 foot 10, and this is 6 foot and 1/2 inch. Now, for the 2 people who didn't make the last group, are you within the group now?
Yeah.
Okay, so I got 100% when the model predicts 99.7. At least we're close there. That's the idea of the empirical rule. Approximately 68, approximately 95, and approximately 99.7 fall within 1, 2, or 3 standard deviations of the mean, going out on either side. And this is true for every normal distribution. I can do the same thing with the males, except it has a different normal distribution. The male sides aren't centered at 65.5, for example. All right, let's go on to the next slide. Actually, let me clear this. So 95% of the data within 2 standard deviations of the mean, and 99.7% of the data within 3 standard deviations of the mean. All right, any questions? May I go to the next slide? All right. Okay, so let's do this again. The test of basic skills for 7th grade students in Gary, Indiana is normally distributed with an average of 6.84 for the mean and 1.55 for the standard deviation. Can we do a quick sketch of this particular normal distribution of scores? Here's how I do this. Here's my horizontal line, and you will get very good at drawing the normal distribution. What value is here at the center? 6.84. Now I'm going to guesstimate that the place where it goes from steep to not steep is about there. So I'll go down, and how much bigger am I going to be at that point? 1.55. So 1.55 plus 6.84, 8 point what? 39. Okay? And by the way, I can also go down 1.55. I'd like a little help doing that. Someone got that for me? It's going to be something like 5.29. Is that right? 5.29. All right. So that quick sketch, we should probably label this. This is ITBS vocab scores. Put a label on this. Yep. All right. So what do we know about this distribution already? About 68% of the scores are going to fall in that range from 5.29 to 8.39. Okay? If I go down another standard deviation from 5.29, guess where I'm going to be? I'm going to guess that I'm going to be at 3.74. Could someone double check that, please? 5.29 minus another standard deviation? Someone confirm that for me? Anyone, please? Dying up here. 3.74? Great. All right. Now they ask us, what percent of the scores are less than that? Oh, this is a little bit more difficult. It's a little bit more difficult question to answer, but we can answer it. All right. Here's how we go about doing that. If I go from here to here, about how much of the scores did I grab? 68. Very good. If I go from here all the way up to 2 standard deviations above the mean, I don't know what it is, how much did I grab? 95% of the data is inside that big wide range. I got a question for you. If I got 95 in the middle, where are the other 5%? On the outside. And because this distribution is symmetric, of that 5%, guess what? 2.5% of it is going to be over here on the right-hand side, and 2.5% are going to be over here on the left-hand side. So guess what? Guess how much of the scores are in that little bitty tail? About 2.5%. Okay, what percent of the scores are between 5.29 and 9.94? Well, by the way, I believe this is 9.94 right here. Well, wait. 5.92 is 1 standard deviation below the mean, and 9.94 is 2 standard deviations above the mean. Does that meet our 68, 95, 99.7 rule? No, only 68 would be 1 above, 1 below. 95 would be 2 below to 2 above. We got to mix and match here. I wonder if we can do a couple more calculations here. To answer this question, how much is in that area? Let's see if we can just do some clever problem solving. From here to here, I'm going to shade it in blue. How much is that again? 68. We're good with that? So blue is 68%. This answer better be bigger than 68 because we're taking a little bit more area. Now, if I go all the way down to 2 standard deviations below to 2 standard deviations above, how much is in the green? 95. So green is bigger than blue. I'm trying to work in a Michigan State joke here, but it's not working.
That's good.
All right? All right? So if that's the case, how much is in this area here and this area here, the places that are green but not blue?
27.
27%? Is that right? Okay. If that's 27, half of that 27 is right there.
Where's the 27?
27 is the area here that's blue but not green.
Oh.
And that area here. That combined area. So half of 27 is 13.5. So in this one little area there is 13.5. So how much is between 5.29 and 9.94? All of the blue plus this 13.5. 68 plus 13.5. 0.5. What? That's a 1 carry. About 81.5% of the population is between those two scores. And this is based on this one empirical rule. I'm going to show you better ways of handling that problem in a little bit. All right, let's go on to the next slide. All normal distributions are the same if we measure units in size, sigma, and mean mu at the center. What does that mean? It means this. Did we have anybody who was any female that was exactly average height, 65 and a half inches tall? No one? Did we have anyone who was exactly one standard deviation above the mean at 68 inches tall of the females? Okay, Jessica, you're 68 inches tall.
Yeah.
Great. All right. And Katya also? Great. All right. So I want to talk about Jessica and Katya for just a second. I have to bring back an idea from yesterday, and that is, what is their z-score? 1. Tell me more, Mr. Braun. Why is it 1? Tell me more. Oh, yeah, z-scores are a measurement of how far you are in the mean, away from the mean in standard deviations. They are both 1 standard deviation above the mean. Okay? Their z-scores are both 1. I can take the distribution of women's heights, and for every height in there, I can translate the height in inches to a z-score value. People who are 68 inches tall end up now getting rescored as a 1. Anyone who's exactly average height, they get rescored as a 0 because they're exactly average. Anyone who was 63 inches tall? Anyone 63 inches tall? Okay. Okay, I want to say it right. Michaela. So Michaela's got a z-score too. What's her z-score? -1. 1 standard deviation below the mean. So what I can do is I can take everyone in that data set, and instead of plotting their height scores, I can plot their z-scores. When I do that, I get a new distribution. That new distribution is still normal because transforming data does not change the shape. The new distribution has a new center, and the new center is at 0. People who used to be average are now a z-score of 0. They're a 0. Okay? People who are 1 standard deviation above the mean, their new score is 1. People who are exactly 1 standard deviation below the mean, their new score is -1. And it's a normal distribution. This distribution with center 0 and standard deviation 1 has a special name. It is called the standard normal distribution. Okay, let me say that again. There are lots of normal distributions, but there's one that involves taking the distribution and translating it to a center of 0 and a standard deviation of 1, and we call that one the standard normal distribution. Every normal distribution that gets standardized, remember how we said the z-score was also called the standardized score? Every normal distribution that gets standardized looks exactly like that, with that center and that standard deviation. Whoops, I don't want that. I wanted to clear the drawing. All right? And again, how do we find the standardized score? We take the data score, given as an x. We subtract the mean. Now using the symbol mu for the mean. And then we divide it by the standard deviation. And again, today, we're introducing the idea that the letter sigma stands for standard deviation. The standard normal distribution is a normal distribution with center 0 and standard deviation of 1. It is a distribution of standardized values. Every normal distribution regardless of its center, regardless of its standard deviation, can be standardized to this particular one single distribution. That's an extremely powerful idea. Why is it powerful? Because now I can give you a tool. Tell me when you're done with this slide, so I can go on to the next big thing. Everyone ready? Nope? Do I draw on your stuff? Oh.
You have the choice to. You just choose not to.
I choose not to be rude.
Right? They had this drawing stuff. Sorry.
Almost ready, Rachel? Ready? Okay, here we go. All right. Again, there's the standard normal distribution. All right. Because all normal distributions can be translated to the standard normal distribution, we can summarize all the information that we need to know into a table called the standard normal table. Okay? Standard normal table is in your book right now, waiting for you. All right? And what it does is it says for any given z-score, for any given standardized score, I can then translate to you a percentile score. Remember we defined percentile, the percentage of data that occurs below this point. Right? This is good stuff. This could be the best lecture of the year. It isn't, but it could be. All right. So, some of you have seen the standard normal table in Algebra 2, I think. Is that right? No? This is all new to you. Yes. All right. But essentially what happens with the standard normal table is it gives us a chance to look at a z and then translate it into a percentile score. So, and this is really where I wanted to have this in front of you in table form, because you guys didn't bring your books today, did you?
I brought my book.
You brought your book? Okay, I'll tell you what. I am going to really, really quickly go to the copy machine while you
So
look
can
at
I
all
get
that
a drink water then?
amazement.
No.
So I'm glad that we got that in the recording, Paul. That's super. I am so very, very pleased. Would you erase that, please?
Do it, Paul. Do it. You're the warrior of this class.
What do you want me to do?
I think that people are going to be having fun with this before.
really stinks. Thank you, Paul. All right. Reminds me of the time I removed the wheels off of one of my teacher's chairs. It wasn't good. All right. So here's the idea. I've got some student, and that student's got a height, and I can calculate their height by calculating a z. Or I can take their height and calculate a z-score. This particular student has a z-score of 0.81. Their height is 0.81 standard deviations away above the mean. Right? What's their percentile? How much of the population are they taller than? Well, to answer that question, we use a z-table. Come on, move. There we go. We use a z-table. The z-table is made up of columns and rows. The first digit here, sorry, these two digits here are found in the columns. The 0.8 are found in the column on the far left-hand side. The hundreds digit is then found by going through the rows. Sorry, through the column. Sorry, 0.80 is found looking down the first column. The hundreds digit is found by going across the top, and then we look for the intersection of the two. Here's the 0.8, and here's the 1. And now I circle the value 79, or 0.7910. This student, who is 0.81 standard deviations above the mean, is taller than 79.1% of the population. Now what you guys want is your very own standard normal table. And this is the gift that I was going to get for you. And what I found is if I leave the room to give you a gift, silly things happen. And I also will be checking the recording to find out, did anyone say, Paul, don't do that. Paul, you're being silly.
Nobody was watching. He didn't even know it's
He
happening.
didn't even know it was happening. He moves like
I didn't
Flash.
know it was happening.
Yeah, we all
He's
changed
so thin. He's like, who's that one kid from The Incredibles?
Oh,
Yeah, she's like this. No one even noticed that he was missing. Now, unfortunately, because the numbers on this table are small, I'm going to have to ask for the lights to be turned back on, please. So if you don't mind, turn the lights back on for a second. Because what I'm going to show you is that this example that I just did is a little bit different on the actual normal table. Okay? First of all, because you're going to have, there's going to be lots of tables we're going to use in this thing, I actually put out all the tables you'll be using in this class. The normal table I made so that if you open up to the inside, 2 pages of normal distribution numbers are in the inside. So open it up like a book. Open it up like a book. All right? You remember this from Algebra 2 or from Pre-Calc? Or from, did you take stats last year, Jennifer?
No.
Jessica? Jessica? You're not Jennifer? Jessica?
My sophomore.
Your sophomore
I
year?
don't remember what
Okay. So when you open it up, it looks a little bit different. And what I want you to do is we're going to do the same problem again, but using the real table. Okay? We're going to do the same problem again, but we're going to use the real table. And I need to bring my table up on the big screen. Statistics. I think there's a folder called Tables. It is. Here's my table. My table is bigger than your table. Here's the Z table. Okay, so we're going to ask the question, what percentage of the population is smaller than a Z value of 0.81? So on your table, look down that first column and look for the, I don't need that keyboard, thank you. Look for the row that's where Z says 0.08. Can everyone find it? It's on the first of your pages. Is that right? Oh, sorry. when you unfold it, it's on the first of those two. Right.
How you doing today?
I'm doing fine. Emily. All right. Now, you look down that and find the point, the 0.8, and then you're also going to see along the top there is a column that has 0.01. Combining those two numbers, 0.81, you see an intersection, and that intersection tells you the percentile score of someone with that z-score. And again, it's still 0.791. So you use the first column as the units and the tens digit. Use the stuff on the top as your hundreds digit. We got it? Do we? I hope so.
We can use this on like tests and stuff.
Okay. Statement. You may use your calculator on every single test quiz in this class. You may use this table on every single test and quiz in this class from now on. I got one more gift to give to you a little bit later. All right. Okay. And last thing that you need to see, and this is down low in the corner here, that combination of z is equal to z is less than 0.81 is equivalent to the idea of drawing the normal distribution, finding the place where z is equal to 0.81, and shading in everything below it. Areas under density curves equate to proportions of population that meet that same criteria. All right, let's try it again. Let's find the proportion of observations under the standard normal distribution that are between negative 0.25 and 0.81. Let's draw a picture first. Here's my beautifully drawn normal distribution. Where's the center? Or what value does the center have? 0. If it's a standard normal distribution, it's centered at 0. Negative 1.25 is about right here. How about 0.81? See, here's about 1. 0.81 is about here. And what am I asking? How much, what proportion is that red drawn in stuff? The table is not going to give you the answer to this directly. Because the table will only do from this point all the way down to the lowest values. Negative infinity, essentially. Here's how we attack this problem. If I want to know what proportion of values are between negative 1.25, here's my z value, and 0.81, and I want you to write it exactly like that, I'm going to start by asking the question, well, how many of the values are below 0.81 all the way down to the bottom? I think we just answered that question. How much is in this area here is what I'm asking, including this little bottom here. This calculation is so essential to almost everything we're going to be doing throughout the year. We've got to get this down now. Don't fade on me. Don't fall asleep. Work with me. 79.1% says Mr. Ron, because we just did that problem. All of the area below 0.81 is 0.7910. But what if I don't want all that area? I want the red area. I want to get rid of this little area here. Is there any way that I can find how much area is below negative 1.25? Answer, yeah, you can look on the z table. There are 2 pages of the z table, one for positive values of z, one for negative values of z. Can you please open your z table to the appropriate page, and let's look for the proportion that's associated with negative 1.25. Okay, I heard some mumbles. So, 0.1056. Now, I have to ask you a question. Does that look to be about 10% of all the stuff underneath the curve? Yeah, roughly. Okay, so we take the big area, subtract off that little black area, and what we're left with is the red area. And indeed, that's how we would do that answer. We end up with, it looks like it's going to be something like 0.68, 64? 54? That's close. Not bad for trying to do it in my head. 6854. All right? So, the z-table is great for reading from this point all the way down, but we can also use it to do problems like how much are in between these two values by taking an upper value proportion and then subtracting off the lower value proportion. Any confusions about that problem? Using the normal distribution to do that calculation. No questions. Yes?
So let's say it was flipped and there was, I don't know, like instead of finding that piece on the left side, what if you had to find the piece on the right side that was on the outside? Would it still be
Okay.
the same? Still
So you want to do this problem? What proportion of z values are greater than 0.81? That's a problem that's different.
Yeah.
Okay. Where is the area under the curve that matches this? It's this area right here. Do you agree? How can we find that one? A z-score from that and above. I could not have said it any better. It's 1 minus 0.7910 because the entire area under the curve is 1, and we're going to subtract off the part we don't want. And then this ends up being what? 0.2090, I think. Does that answer your question? Excellent. Excellent question, too. All right? Okay. How much time do we have left?
2 minutes.
2 minutes. Okay. Let me tell you how we're going to do this. I know I'm not going to see most of you tomorrow because of the senior breakfast. Is that correct?
Yes.
Okay. But we did not complete this lecture. I'm sorry to say. Here's what I ask of you. All right? I have all of about 4 slides left on this lecture, and it's relatively easy material. I'm actually going to do the lecture tomorrow with the students who are here, the non-seniors, and I'm going to post it up to the website by the end of 3rd period tomorrow. Okay, I'm going to ask you, even though you have a very, very busy weekend planned, to watch that 15-minute lecture. Monday is the quiz day. All right? So you're going to need that information to complete your knowledge.
You do know some skills.
You know, I mean, what I really want to, I need to get the test done before, on Wednesday, because otherwise we're holding over on a 4-day weekend, and that's bad. No one is going to do well on a test after a 4-day weekend. All right, is everyone cool?